In the earlier class, we studied non-coherent binary FSK, and we also said that the results can be extended in principle to any non-coherent binary orthogonal signaling scheme. Today we will study non-coherent version of PSK, which is popularly known as DPSK, that is differential phase shift keying. In the normal BPSK transmission, we have two antipodal signals S1T and S2T, which are being transmitted say for symbol 1 and 0 respectively. Now, we assume at the receiver that there is a synchronization between the transmitter and the receiver, in which case the optimum receiver is a coherent receiver, which is depicted in this figure, which we have studied earlier. So, we have a reference signal out here, which is in synchronization with the transmitted signal. Now, if we have a phase uncertainty in the received signal, then we will get the following model for the received signal. We have the received signal, which is plus minus cosine with a phase uncertainty and additive white Gaussian noise as usual. Now, if this is the received signal and if that signal is demodulated using this coherent receiver, then we will get at the output this signal contribution from the received signal will get multiplied by cos theta term, and depending on the value of theta, the output will vary. So, there will be uncertainty about the contribution from the signal component itself in the received signal. So, to take care of that, we can provide the following solution, provided we assume that the phase variation between the two consecutive signaling interval is slow enough. So, what we could do at the receiver, as a local oscillator, we can choose the delayed version of the received signal itself. In that case, our reference signal, which will serve as a local oscillator, would be given by this term, where RT is this signal, including the additive white Gaussian noise. Now, the output here RK will consist of the following terms. You will have plus minus E, which is a contribution from the signal part. Here again I repeat, this does not have any theta term, because we are presuming that at this point and this point the phase cancels out because of the slow variation, and then these are the three noise terms. So, Wk and Wk minus 1 are the usual noise terms. Wk is the projection of the input Wt onto this signal, Wk minus 1, which is the projection of this noise onto this portion of the received signal, and this term is equal to the cross product term between the two noises delayed by Tb duration, and this is zero mean symmetrical PDF. Okay. So, for this configuration it is easy to observe that Rk will be greater than 0 when present bit equals previous bit, and Rk will be less than 0 when the present bit is complement of the previous bit. So, your decision would be as follows. Now, the problem with this decision making process is that if one bit goes wrong, then there is a cumulative effect, because the decision is based on the previous bit. So, in order to take care of this, we could do differential encoding at the transmitter end as follows. If present bit is 1, then while transmitting I advance the previous phase by pi radians or 180 degrees, and if the present bit to be transmitted is 0, then the previous phase remains unchanged. If we use this strategy of differential encoding and then use phase shift keying for transmission, then it is easy to see that this scheme will work with the following decision process. Now, Rk will be equal to E plus some other noise terms will be there, and this will happen if 0 is transmitted, and Rk will be less than 0, that is minus E. This is signal contribution if 1 is being transmitted, because we have used the following encoding procedure. So, decision rule would be Rk greater than 0 implies that I decide in the favor of 0 symbol, and when it is less than 0 I say that 1 has been transmitted. Now, the disadvantage of this procedure is that we have additional noise terms. So, the signal to noise ratio has deteriorated. So, the question is it possible to find an optimum receiver for DPSK? Now, we can observe that in DPSK the transmission in the current interval is based on what has happened in the previous interval, in the sense that if I want to transmit symbol 1 in the current interval, then I will have to change the phase of the previous transmitted signal, and when I am transmitting the symbol 0 in the current bit interval, then my earlier phase remains unchanged. So, now if you look DPSK signal over duration 2 TB, we will get some additional information. So, before we do that, let me define two signals, x1t, which is a cosine with a frequency fc, and x2t, which is antipodal of x1t. Both these signals are of duration Tb, and for sake of brevity I denote x1t by just x1 and x2t by x2. Now, if I see the DPSK signal, then let me define signal S1t as the transmitted DPSK signal which is for the duration 2 TB, and this S1t is for the case for transmission of binary symbol 1 at the transmitter input for the second part of this interval, that is between TB and 2 TB. So, the transmission of symbol 1 advances the carrier phase by pi radian. So, what it means that my S1t signal over a duration of 2 TB for the transmission of 1 will consist of x1 followed by x2, or it could be x2 followed by x1. So, the symbol is being transmitted during the second part of this interval 0 to 2 TB. So, it will change the phase. So, if it was x1, it will become x2, and if it was x2 and x1. So, similarly, let S2T denote the transmitted DPSK signal again for the duration 0 to 2 TB for the case when we have a binary symbol 0 at the transmitter input for transmission during the interval TB to 2 TB. So, the transmission of 0 will leave the carrier phase unchanged over the interval 0 to 2 TB, and so we define S2T as x1T followed by x1T, or it could be x2T followed by x2T. Right. Now, xi and xj are taking values ij from 1 or 2, and it means that xit is followed by xjt. So, the first TB second of each waveform are actually the last TB second of the previous waveform. Now, having defined this S1T and S2T over the duration 2 TB, we see that S1T and S2T can each have either of two possible forms. So, it could be either this pair or it could be this pair. Correct? So, any pair you take from these two pairs, it is not difficult to see that because x1T and x2T are antipodal signal, S1T and S2T are orthogonal over the duration 2 TB. So, what this implies that pairs of DPSK signals can be considered as orthogonal signals when we consider 2 TB long duration. So, now we can extend what we have studied earlier for non-coherent binary FSK case. We said that it is extendable to non-coherent binary orthogonal signaling scheme also. So, detection now could correspond to non-coherent envelope detection with 4 channels match to each of the possible envelope outputs. We have 4 cases here, correct. So, based on this reasoning, we can have the optimum receiver for the DPSK signal with the phase uncertainty as shown in this figure. So, this corresponds to the transmission of symbol 1 during the second part of the duration of 0 to 2 TB, that is between TB and 2 TB, and similarly this corresponds to a transmission of symbol 0. Now, note that the 2 envelope diffractors representing each signals here and here are negative of each other. So, the envelope sample of each will be the same. Here the envelope sample, here it will be same, and here will be the same. Therefore, we can implement the detector as a single channel for S1T matched to either X1 X2 or X2 X1, and a single channel for S2T matched to either X1 X1 or X2 X2. So, DPSK detector is therefore reduced to a standard 2-channel non-coherent detector as shown in this figure. Now, in practice, the filter can be matched to the different signal so that only one channel is necessary. This figure can be expanded as shown here based on what we have studied earlier. We have phi 1 IT, phi 1 QT, and similarly phi 2 IT, phi 2 QT. To obtain this R2I and R2Q, and this signals phi 1I, phi 1Q, phi 2I, phi 2Q is given by the expression shown here, correct. Remember, these are orthogonal to each, this is orthogonal to this. Similarly, any of this signal is orthogonal to any other signal out here. So, now the probability of error for such a optimum receiver could be obtained very easily based on what we have studied earlier for the non-coherent BPSK. The only difference is that TB will become 2 TB and your energy will become twice the energy, because we are talking about the duration which is 2 TB. So, we know that probability of error for binary BPSK case was given by half exponential minus E by italic n. So, now in this case our E will become 2E, right, because we are talking about duration 2 TB, and we get this is the relationship for the probability of symbol error for the non-coherent PSK or DPSK. So, we see that DPSK requires 3 dB less signal to noise ratio per bit for the same performance as compared to the non-coherent binary FSK. Now, with this we come to the end of our study on digital modulation. So, let me summarize our study of digital modulation. We began our study with coherent binary ASK, binary FSK and binary PSK modulation schemes. We showed that binary PSK is efficient in terms of signal power. It requires 3 dB less signal to noise ratio per bit compared to the binary ASK or binary FSK case. Binary FSK requires a larger bandwidth compared to the binary ASK and binary PSK. Then we extended our study to bandwidth conservative modulation schemes, and we studied QPSK and its variant and MSK. We saw that performance of all these modulation schemes is comparable to the binary PSK. MSK has constant amplitude, continuous phase and lower side lobe levels and easy to demodulate mechanism like the FSK modulation scheme, and that is why it is quite popular in mobile communication applications. And then we moved over to the study of Emery modulation schemes. We saw that Emery ASK, Emery PSK and the hybrid versions of this two amplitude and phase modulation is COM. All these three modulation schemes are applicable in applications which are bandwidth limited, and in contrast we studied Emery FSK modulation which can be applied in applications which are power limited. We studied that in Emery FSK, as the size of the constellation increases, for the same error performance, signal to noise ratio per bit required decreases, but at the expense of bandwidth. And then lastly, we studied non-coherent modulations, and we concentrated only on two of this, and these are binary FSK and binary PSK, that is non-coherent binary PSK is also known as DPSK, differential phase shift keying. And we saw that differential PSK requires 3 dB less SNR per bit for the same error performance compared to the non-coherent binary FSK case. And both this non-coherent modulation schemes are special cases of a general non-coherent orthogonal signaling scheme. So, with this we conclude our study on digital modulations. Thank you.